Oh, that's too bad. I was enjoying the music. Welcome, pre-calculus trig students. We're doing parametric equations today. These are going to be probably something you've never done before. So take out those notes and let's go. First, we're going to pretend that Davis is throwing the ball at a 45-degree angle at an initial velocity of 48 feet per second. So if you were doing this equation in your normal mode, the way that you know how, your equation might look something like this, and your graph would look something like this. Now this equation tells you where the ball has been, however it does not tell you when it was at each position. So you might know, for example, that the ball was here, 15 feet across and 12 feet in the air, but you don't know when it got there. Well, with parametric equations, we are going to introduce a third variable of time. Now notice with parametric equations, you're going to have an x equation and a y equation, and then another variable which is going to be t. T is going to stand for time. So for example, right here, when the ball makes it 36 feet across horizontally, it's 18 feet in the air, and it occurs at the time 3 square root of 2 over 4, whatever that is in decimal form. Alright, so that's an example of parametric equations. This talks about plane curves. We're not going to worry so much about that right now because we need to get into being able to do this. So take out that calculator if you don't already have it out. We're going to use that in a moment. But first, let's just do this by hand, and then we'll show you what to do with the calculator. So this tells me our domain for t. Alright, so t is between -2 and +2. I'm just going to pick some integers between -2 and +2, like -2, -1, 0, 1, and 2. Now maybe if I draw this and there's not enough detail between a couple of these, maybe I'll need to insert some more. You just have to kind of go with the flow here, and if you can't tell what the graph is doing, go ahead and plug in some numbers in between what you've chosen in order to get a better, smoother graph. Alright, so let's do the x. X looks easy. X and t are exactly the same according to this equation here. So all we're going to do is, since x and t are exactly the same, we're just going to copy this number right here for x. Super easy. Alright, done. Alright, now t is going to be a little bit harder, or I'm sorry, y is going to be a little bit harder. We're going to take -2 times t in order to get our y's. So we're going to take -2 times each of these numbers. So -2 times -2 gives me 4. -2 times -1, 2. -2 times 0, -2 times 1, and -2 times 2. Alright, there, you can see the 4. Alright, so this is the same as normal. We're going to plot just the points x and y, just like these are normal points, because they are. Alright, so there's all of your points. You can think of them like this if that helps you. So let's plot the point -2, 4. That goes there. -1, 2 goes there. 0, 0, 1, -2, and 1, -4. Alright, so now we're just going to include the variable t. This is going to be time. So like, let's pretend that, I don't know, some sort of explosion happens right here at time 0. We want to see what happened 2 seconds before the explosion and 2 seconds after the explosion, maybe. Something like that. Who knows? So right here, this is where t equaled -2, because that was the point, -2, 4. This is where t equals -1. T equals 0 was here, t equals 1 is here, and there's not really any magic where you're putting these, just make it so it's readable, just like that. Now we're going to connect our dots, and we're going to pray that I can somehow draw a straight line. Almost. Hey, not too bad. Alright, and as we're drawing the straight line, this is going to have direction, because this is time -2, this is time +2, so our direction is going this direction. As time's going past, we're going down and right for this one. Alright, so you just need to draw some arrows in there just to show you which direction you're going. And that's all there is to it. Now, you may need to bust out that calculator of yours, and we're going to do something you've never done before. Alright, press the on button. Next, you're hitting mode. And maybe I should type this for you as we're going. So you're typing mode, and you're going to choose parametric. You've probably never used this one before. That's okay. It's going to be new for everybody. So mode, not model, sorry, model's more like me. Mode parametric. And once you have parametric mode, then go on down. Let's make sure we're in, right now we're going to be in degrees mode, so let's leave it in degrees. It doesn't really matter for this particular problem, but for right now I'm going to say let's stick with degrees. And everything else you'll pretty much leave the same. Alright, so now that you have that, I want you to hit y equals. Once you're there, clear out anything, and you should notice something crazy has happened. Instead of our normal y1, y2, and all that stuff, we now have an x and a y, right? So instead of x, or after the x equals, you've got that little t down there. That just means your variable is going to be t. So after the x equals, you're going to put in the x equation. In this case, it was just t. Now you're wondering, where is the t? Take out your calculator. You know where x normally is? That's the button you want to press. And when you press it, you should notice that it's a t. Huh. Then for the y equation, you're going to write what the y equation was, which was -2t. Again, instead of t, you're going to press where you normally press to get the x. And you'll notice that with that x button, there's a t there. You've just never used it before. Alright, after that, let's change the window. So let's go to window. We've already done the y equals, so let's go to window. And for this particular one, our t's were between -2 and 2. So what I want to do is put -2 for my minimum for t. My maximum is going to be 2. And then what do you want it to count by? Well, if you have a big number, like let's say 1, that t-step number is telling you how often your calculator is going to snap a picture of where your dot is on the line as it's traveling. So here's what this means. If I have number 1, it's only going to snap one shot each second. So it'll take 1 second for each shot. So this line that we just graphed is only going to have 5 dots to it, right here, 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 and here. Now it's not a big deal if it's a straight line. However, if this were a curvy line, then it's going to make your line or your function look really strange. So right now I'm going to tell you for that t step, you want it to be a really tiny number. You want it taking lots of photographs. So if you wanted, for example, a motion picture, maybe in your cell phone or whatever, it takes 30 frames per second. So it would be something really small. So like, I'm going to do 0.1 on my calculator. So go ahead, use 0.1. This means that every 1/10 of a second, we're going to take a snapshot on your calculator, and then your calculator will connect all the dots. If you put 0.01, that would be even smoother. It would just take your calculator a little more time. Alright, now for x, we can kind of cheat now because we already know what the x values were. They went between -2 and 2, which was easy to see. So if you want to, for your x minimum, you can go between -2 and 2. Honestly, I would just do a nice little generic -5 5, and then count by ones for your x scale. Alright, for your y's, I would go -5, 5, and 1. Now, if these don't appear on your graph, so let's say your graph falls off the screen so you can't see it anymore, then go ahead, change the window. It's totally up to you. For some of these word problems, these might need to be in the thousands. You just have to be smart enough to know what window to use. Okay, now you should be able to hit graph, and when you do hit graph, you should have a graph of this function. Amazing. Alright, so next let's do another one. This time we'll let you either do it in the calculator or by hand. It is up to you. It's not too tough to do this one by hand, so I'll do it by hand. Alright, this time it tells us that our time window, our time frame, is between -2 and 3. So I'm putting in -2, -1, 0, 1, 2, 3. It tells me that x is t squared minus 4. So -2 squared minus 4 is 4 minus 4. -1 squared minus 4 is 1 minus 4. 0 squared minus 4. 1 squared minus 4. 2 squared minus 4. And 3 squared minus 4. That was pretty easy to do. Next, it tells me that t divided by 2 is going to be my y. So -2 divided by 2. -1 divided by 2. 0 divided by 2. 1 divided by 2, 2 divided by 2, and 3 divided by 2. Easy, right? Okay, now we're just plotting the points 0, -1. Now notice, since this was t squared, we're going to have a curvy line, so that point 1 is going to be really important for your t step. Now I've got -3, -1/2, so 1, 2, 3, -1/2, -4, 0. Ooh, and it might be a good idea for me to just label these as I'm going. There's -2, there's -1, there's 0, and there's my 1, and 2, I totally screwed that up. I am so sorry. I started just doing it from memory, and my memory is not so good. There's my 1. Sorry. There's my 2. And my 3 is 1, 2, 3, 4, 5, 1, 2. There is my time equals 3. Now we're going to connect the dots. Oh, this is my most terrifying part. I'm going to try to connect these. Eek, eek. Alright, this is really hideous with the pen pad. Sorry. You know, on the board this would have been beautiful, but this is what we're stuck with. So we're going this direction, so I'm going to draw little arrows. That's a -1 there. It's hard to see. So at -2, I'm traveling this direction. There's 0, and at 0, suddenly things take a turn. And we go that way. Alright, so that's it. Either you did that on the calculator or with your hands. Now we have something called eliminating the parameter. When you eliminate the parameter, you're going to solve one of them for t. I'm going to suggest doing the x1. Do that one, solve that for t. We're going to substitute it into the other equation and then simplify to find the rectangular equation. This sounds scary, but it's not so bad. So here we go. This first one, we're going to solve this for t. Alright, so what do I do to both sides? Well, a nifty trick is to take them both and flip them upside down. You're allowed to do that. What you do to one side, as long as you do it to the other, you are a-okay. Now that I have that, I need to get rid of the square root, which can be done by squaring both sides. So I square it like that. That gives me 1 squared over x squared equals the square root of t squared is t. Alright, so now I know what t equals. Now I'm going to go back up to my y equation. Every time I see a t, I'm going to substitute 1 over x squared. So I'm going to copy what I had to blank squared. Instead of t, I leave it blank. And then inside that blank, I'm substituting the 1 over x squared, because t and 1 over x squared mean the same thing. So there's 1 over x Oh, I almost misspelled x squared. Now we are good to go. I have y equals 2, then in parentheses 1 squared is 1, x squared squared is x to the 4th, and then we can simplify that a little bit more. That gives us 2 over x to the 4th. That is my rectangular equation. What does it mean by rectangular equation? Well, rectangular just means there's only an x and a y, and that's it. It does not mean that the graph of this becomes a rectangle. Now, before we move on to the next screen, something very important up here to notice is that we really should have created a domain right here. I needed to know that from the very beginning, our t value has to be 0 or bigger. So I know that t has to be greater than or equal to 0 here, and the reason why is because if I put a negative number in here, I'm going to have an imaginary number. Now I know we've been doing imaginary numbers in the past, but for our sake, for parametric equations, we will not use negative numbers. Hold on, I'll give you some time to cheer. Alright, climb down off the desk. It's going to be okay. Alright, so t is greater than or equal to 0. Now I know if this number is positive, then I know that my x value here, because of this, if this is any positive number or 0, well, actually, wait a minute. What are we thinking? If this is 0, I've got 1 divided by 0. So that's not going to work either. So let's get rid of the equal sign then. Okay, so now not only was it in a square root, so it had to be 0 or bigger, it's in the denominator, so denominators have to be bigger than 0 or less than 0, but we already ruled out the less than part. So this one, this whole function, has to be greater than 0. Now, if this is a number bigger than 0, I've got 1 divided by a positive number. So I know that x also has to be a positive number. So down here for my domain, I know that x has to be a positive number, so I'm going to put x greater than 0. So that is my domain for this whole thing. X has to be bigger than 0. And that's all there is to that one. You just now know that we cannot put in a negative number. So if you graphed this and this on the rectangular world, or I'm sorry, in the parametric world, you would get the same as if you graphed this one. Let's show you how that works. So on your calculator, let me go back. On your calculator, go ahead and type this thing right here for your x value, and then for your y equation, you're going to type that in and hit graph. After you do that, you should have a few points on there. Well, not very many points, to be honest. I'm going to drag this down so I have enough room. So I've got 1, 2 is where t equals 1, and t equals 2 here at 1, let's see, t equals 2 up here at 8, 4, 5, oh my gosh, 6, 7, 8, t equals 2 is like right here. So this makes it kind of difficult to figure out if we're just doing parametric, but if you graphed it, you saw that it's going to do something like this. Let's see if I can graph it well. And then something like that. Alright, and again, since this is time equals 2, time equals 1, oops, I put my arrow in the wrong spot. Let's try that one more time. My arrow should have gone that direction because we're increasing in time. Just like that. Alright, if you wanted to, you could change your window settings slightly by hitting second window, and that'll give you a different table. Where you have the delta or triangle looking thing, when you have the delta t, you could put in something like 0.25. If so, you would have noticed that 0.25 is right here. Again, that wasn't necessary, but it's just a way to make it so that your curve is a little bit nicer and you can see where the points are. Alright, now in order to see that this graph really does work out this way, and that you really did do this correctly, go back to Mode on your calculator, hit Mode, and go to Function, or as my calculator says, Func. So go to Func Mode, and it should now, when you hit y equals, it should now just say y1 equals, and you're going to press 2 divided by x to the 4th. When you do that, you'll graph it, and it should look just like this, except it also has something over here. But remember, because of our domain right here, x could not be greater, or could not be less than 0. So we're not going to look at these points over here on this side. We're only looking at the places where x is greater than 0. But it should match perfectly. Okay, now let's practice with one more. I'm going to let you hit pause and do this. Just graph them, and then hit play when you're ready. Alright, hopefully you are ready now. So in order to do this, I'm going to solve both sides, or solve both of these. I'm going to start with 1 over x equals square root of t plus 1. And I can put it over 1 if I like, it doesn't really matter. All I did was flip both of these upside down. Next, I want to get rid of the square root, so I'm going to square both sides. So this gives me 1 over x squared equals t plus 1. Now, next, t plus 1, I need this to be t, so I just need to subtract 1 from both sides. So that gives me 1 over x squared minus 1 equals t. And that's it. Now that I have that, I can substitute this every time I see a t in the other equation. This is going to be a little bit trickier because we have t's on top of t's. That's okay. So I've got y equals blank over blank plus 1. Now in the first blank, I'm going to substitute this stuff in pink. 1 over x squared minus 1. And then here, guess what? The same thing, 1 over x squared minus 1. Something magical does indeed happen on the bottom, if you notice. We've got negative 1 and plus 1. These will cancel. That's nice. Now I have 1 over x squared minus 1 on the top. I can flip this upside down and multiply, right? So that would be times x squared over 1, or just x squared. Now that's the same as if I wrote this in front, it doesn't really matter. My next step, I can just distribute this to both of these. So now I have y equals x squared over x squared, which is just 1, minus 1x squared. And that is my function in rectangular form. Again, if you're not sure if you did this right, go ahead, graph these in parametric mode, graph that in function mode, and they should match exactly. But before we continue on, let's not forget about the domain. Here in the very beginning, I know that this number has to be the t plus 1, the number under the square root, has to be greater than or equal to 0, because everything in a square root has to be greater than or equal to 0 for it to be a real number. However, again, since we're in the denominator can never equal 0, so we're going to get rid of that equal sign. Therefore, we know that t has to be greater than negative 1, because I subtracted 1 from both sides. Alright with that? Great! Now that I know that t is greater than negative 1, I can move on over here. I know that when I do this work, I know that's got to be greater than negative 1. So I can add 1 to both sides. That gives me 1 over x squared is greater than 0. So, ooh, my face. So then I'm going to solve that. So I could just multiply both sides. Oh my gosh, I've got a mess here. So I know that x squared cannot equal 0. So good news, I know no matter what's going to happen, I'm going to end up with a positive number for this. And we kind of knew that already, because if I put in a number here, even if it's negative, it's going to square and it's going to be positive. Alright, so now that I have that, I am ready to graph. Let's go ahead and graph, and remember we're only graphing where x is going to be positive. So let's plot some points. You should have your t equals 1 was right about here, and your t equals 0 was right about here, and that's probably about all the points you were able to get. So if you were going ahead and doing decimal values for your t steps, I noticed that this nice pretty value was where t equaled negative 0.75. So again, a helpful tip, if you're not able to get very much out of your graph from your chart, from your XY chart, then go ahead and make your t step small, like maybe 0.25 or maybe 0.05 even. It'll just give you some more values to choose from. Again, to do that, you hit second window, which is the table set, change your delta t to something smaller, like 0.05, 0.25, something like that. Alright, so there's a smaller number. This is a bigger number, so I know that my arrows are going to go this direction. And if I were able to draw a nice pretty line on this, this would look beautiful. But it looks something like that. Alright, again, if you do the same thing with the rectangular equation, you should get the same looking graph. Next, we're going to go into crazy land. We're going to insert some trigonometry just when you thought it was all gone. More trig coming your way. This time, in order to solve for, in order to eliminate the parameter, we're going to let the parameter be theta this time instead of t. Great news, if you speak Greek, this is just t anyways. Alright, so my goal is to get cosine of theta and sine of theta all by itself. Let's do it. In order to do that, I've got 2 times the cosine of theta. I don't want them touching each other because that's gross, so I'm going to divide both sides by 2. That leaves me with this. Okay, now I'm going to do the same thing over here. We're going to leave this here for now. You'll see why in a minute. Again, I have a 2 touching the sine. Those are not always the same number. It was just kind of a coincidence. Mostly just because of the shape that I want this graph to be. Alright, and I have that information. This time I go ahead and I give you what the timetable is, except instead of time, these are actually angles. So I give you the domain for the angles. You can think of it that way. Alright, now going way back to our trig proofs section, everybody, probably even yet still, remembers that sine of theta plus cosine of theta equals 1. Well, let's do some substituting. Instead of cosine, I can put x over 2. Oh, and both of these are supposed to be squared. Sorry about that. Cosine squared plus sine squared is 1. So, there's cosine squared plus sine, which is y over 2, all squared, equals 1. Now that you know this, we can go ahead and simplify a little bit. This is x squared over 4 plus y squared over 4 equals 1. And if you remember back to first semester when you had that really awesome teacher who's even better looking than I am, you'll know that this should be the shape of a circle because the a and b values down here are equal. So let's go ahead and multiply this whole darn equation by 4. When I do that, that gives me x squared plus y squared equals 4. X squared plus y squared, this means it's a circle. 4 means your r squared is 4. That means your radius is 2. So this indeed is the shape of a circle. So all we're going to do is make a circle with a radius of 2. Easy, right? Now we know my drawing on this thing is pretty awful, so I'm going to cheat a little bit and draw a circle this way. You're welcome. Alright, close enough. So now that I have this circle, I'm going to go ahead and think of what my theta values are. This is where, oops, I misspelled theta, sorry. This is where theta equals 0. This is where theta equals pi over 2. Here, theta is pi, and then this is where theta equals 3 pi over 2. Now if you're confused about this, this is your unit circle. You already know this stuff. Alright, and that's all there is to that one. Again, you are more than welcome to graph this on your calculator. If you're graphing it already and you're wondering, why does my graph not look like this? You need to convert to radians mode whenever your stuff is given to you in radians, such as this. You know this is radians because your theta is between 0 and 2 pi. Alright. Now we're going to sketch a similar curve. I'm going to go ahead and hit pause. You're going to hit pause. I'm going to wait. And then when you're ready, after you finish this, go ahead, hit play again, and I'll be here. Okay, my hope is that you've divided both of these by 3. You've divided both of these by 4. On the side, you got x over 3 equals cosine of theta. Here you got y over 4 equals sine of theta. Oops, there we go. You remember that cosine squared plus sine squared equals 1. Then you simplify. This is x squared over 9 plus y squared over 16 equals 1. Now, hopefully you were realizing these two are not the same. Unlike the previous one, these are not the same numbers. That means it cannot be a circle because the y value, or the height, is going to be bigger than the width. What shape does that give you? An ellipse, that's right. So this is going to create the shape of an ellipse. Remember, we're square rooting these, so your a value, you would be 3, and the b value here would be 4. So let's move on. Going across was 3, y across, because that was with the x was on top of it, and then your y had a 4 under it. Well, really a 16, but there you go. When we square rooted, it gave us 4. I'm going to cheat a little bit again and use my ellipse tool. Oh my goodness, it's a masterpiece. Alright, right here I have theta equals 0. And I'm labeling this the exact same way as I did last time. Why is that? Well, because theta's the same. It's not going to change. It's in the same place. And that's all there is to it. Oh, now last time I may have forgotten to draw my arrow. So as theta is increasing, it's going counterclockwise, just like that. I may have forgotten that last time. Sorry, I hope you forgive me. Alright. That's all for that page. Now, let's move on to my next slide. There we are. We're going to find a set of parametric equations to represent the graph of y equals 1 minus x squared using parameters. Are you ready? Yes? Great, I knew you were. So right here, I've got t equals x. So every time I see an x right there, I can just substitute t. So I've got y equals 1 minus x squared. But instead of x here, this tells me that x is the same as t. So I'm going to put t. And wow, look at that. That one was rather easy. 1 minus t squared is the equation. That's all. Alright, so I've got t equals 2 minus x. I need to solve for x. So that's going to give me t minus 2 equals negative x. I can multiply everything by negative 1. That gives me 2 minus t equals x. Woohoo! Alright, I've solved for x correctly. I've been very careful about my negative signs. And now I am ready to plug this in to my other equation. Remember, my equation that it gave me right here was y equals 1 minus x squared. You'll notice my blank that I left a lot more room. Why is that? Because this is, it's going to need a lot more room than just an x. So, or just a t. 2 minus t is what goes here. Next I have to do some foiling, so let's do, this is going to stay in parentheses because notice it has the minus in front of it. So let's go ahead and do 4 minus 4t plus t squared. This was me foiling it out. If you stink at foiling, go ahead, write it twice. Just like that, and then foil it out like that. Either way is good. You should still get the same answer. Next, let's distribute our negative through. Minus 4 plus 4t minus t squared. Whew, almost there. So now I have y equals, let's put it in standard form just to make life easier. There's negative t squared plus 4t And then this, the 1 minus 4, gives me minus 3. Woohoo! We did it! There is our function. Alright. I hope you've enjoyed that. Now let's move on to what else? I've already shown you the graphing calculator. Now it's time to move on to cycloids. Cycloids. This is when a path is along the edge of a circle and its path is going to be traced out as the circle is rolling across a straight line. So think of this as a piece of gum that you've run over and it's stuck to your bike tire. And we're going to just graph where the gum is along the horizontal axis and the vertical axis over time. So here's what it would look like. Here's what it would look like. Any moment now, it's going to work. You know what? This is pretty much a whole disaster. Here we go. This is going to work. There we go. Whew. These special effects are fantastic. Alright, so that's what a cycloid looks like. We can do a cycloid. Here's one. It can be represented by 2 theta plus sine of theta, and y, 2 times 1 plus cosine of theta. Here you go. I've given us the domain restriction. We're going to go between 0 and 5 pi. So let's go ahead and graph this. You're going to press y equals, and well, if you're not in parametric mode, first you're going to hit mode and then parametric. Then you're going to hit y equals, and on x equals, you're going to type all of this in. Where it says theta here, you're going to press x, and it'll say t on your calculator. That's okay. Same thing there. Then for the y equals, you're going to type in this stuff, the 2, and then the parentheses and all that junk inside. And again, where it says theta, you're going to put t. Now you should be ready to graph. Let's do it. First point you have should be 0, 4. And then you should have a point at 2, 0, 4, 4, 6, 0, 8, 4, 8 pi, I should say, 4. And then here at 10 pi. So notice these are counted by pi's. If you didn't do this already when you saw that pi, you should change your window so that your tick marks are counted by pi. Alright, now this doesn't give me quite as much information as I was hoping. So maybe I would type in something for my t step so that it's something a little bit smaller. Maybe 0.5. If you do that, you'll get this. You get some dots in between here. And then it starts to kind of look like you would expect it to look. So you're going to draw, oh boy, this, and then it'll come back up. Alright, you get this. This is so painful to have to draw this on here. Alright, something like that. Oh geez. Alright, there you go. So something to that effect. Oh, that drawing was terrible. I'm so sorry. On, we're moving to projectiles. This one is my favorite part. So right here, I don't know if this appeared correctly on yours because on my copy it fell off. So just make sure that this equation is correct for yours. V sub 0 is the initial velocity. Cosine is our friend. We know him. T is time. H is going to be height. V sub 0 again is initial velocity, just like there. Sine of theta, you know him. He's our friend. T is still time. Now why is this negative 16 here? Because that's the gravitational pull of the Earth. It's always going to say negative 16 as long as we're on Earth and we're not using the metric system. Alright, it looks like Jacob is shooting Claire out of a cannon from their second floor on their house, which is 10 feet above the ground. It's going to be shot, or she's going to be shot at a 60-degree angle toward a soft landing target that is 1,090 feet away. I think you should hopefully have a blank there, horizontally. The initial velocity is 200 feet per second. Will she land on the soft target? Excellent question. So let's go back here and look at our equations. These are our formulas, and I'm going to copy this and then paste it, just so I have enough room. Boop, like that. So let's use our information to create equations. The initial velocity we said was 200 feet per second, so I'm going to put 200 right here. Cosine of 60 degrees, because you said it was at an angle of 60 degrees. And then t is time, we don't know what that is. For our other equation, we have y equals, h is our starting height. We were starting 10 feet above the ground. Our initial velocity again is 200. Our sine is our friend, and then theta again is 60 degrees, and t. Now, you have noticed, hopefully, that we have used degrees here, so that means you're going to have to hit mode and degrees. If you're not already in parametric mode, make sure you're also there too. Now that you have this, you are A-OK to type y equals on your calculator. When you do that, you should be able to put this in for x and this in for y. Go ahead and do that. Before you hit graph, you're going to need to change that window. So this says she might land 1,090 feet away. So because of that, this is horizontally, so this means that our x value has to go between 0 and at least 1090. So I'm going to be going to 1100 just to make sure I can see that whole graph. And in fact, I like to see where it really starts, so I like to give myself a little bit of room on the left so I can see the x-axis and the y-axis. So I'm going to put -10 there. So my x minimum, -10, maximum 1100. This way I'll be able to see everything. Now, how high will she go? I don't know. They're shooting her at a 60-degree angle. I'll just guess. Maybe I'll go from, again, I like to give some negatives there. Let's go -10 up to, I don't know, let's see if 600 is enough. If not, I can always change it when I graph. So that would be my y. Alright, now there's a t also to worry about, and my t, I don't really know. Now this is time in seconds, so I don't want to know what happened before we launched her out of the cannon, because that mathematically is not going to be correct anyways. Before we launch her from the cannon, she's just going to be sitting there. So I know it's going to start at 0, and I don't know, how many seconds do you think it'll take to launch her? Well, if you pick something too small, like let's say 0.5 I know is too small. If you pick something too small, it'll start to graph it, and then it'll stop. And she'll never reach the ground, she'll just be hovering there in midair. And that's because your calculator's taking pictures only for the first 0.5 seconds. And then after that, camera stops, so you don't know what happened here. Therefore, we need to pick something that's big enough so that we'll get the whole trajectory, we'll see what happens and where she'll land and all that stuff. So I figure it should take no longer than maybe 8 or 9 seconds for her to go that far. I'm just going to put 8. If for some reason 8 doesn't work, and let's say it just stops there, even though the ground is down here, then I would just pick something bigger, like switch it up to 10. Alright. Once you've done that, you should be able to go ahead, hit second window. This will change your table set. You probably want your table set to start at 0 and count by ones. Now you should be able to hit graph and see what it looks like on the graph, or you could even hit second graph, which will give you the table, and that way you can see where she is relative to time in different spots. So for example, on my TXY chart, at time equals 0, she should go nowhere, and she should be 10 feet above the ground. This is an easy way to check your answer to make sure you've done this correctly. If you have those, that's probably a good sign, because you knew this in your head already. After 1 second, she's 100 feet away horizontally and 167 feet up. 2 is 200 and 292, and so on. Eventually, you get to the point where she's at 10 seconds and She's going 1,000 feet horizontally. She's at 142 feet in the air. Now notice, if we only had 10 for our time, that wasn't enough because she's still in the air. So I'm going to have to expand it out. At 11, I notice that she's gone horizontally 1,100 feet, and she is negative 20, I can't read my writing, but it's negative 20 something feet below the ground. So therefore I know that if I was hoping to make it 1,100 feet, that's not good, because she's already hit the ground. In fact, she's burrowing under the ground, creating a giant crater by the I don't know, gunpowder and the force that she has going into the ground. Alright, so I know that she's hit the ground somewhere between 10 seconds and 11 seconds. It's going to be closer to 11. If you did graph this, your graph should look like this. You could very simply find this point by doing some intersection work on your graph. Alright, hopefully you have played along with me and you have checked this out and you totally agree with everything that's here. If you have questions, go ahead, you know where to find me. You've got my email address, you've got my office hours with my Zoom chat and all of that. I hope you're having a beautiful day. Don't forget to do that homework and make sure you hit all the deadlines and turn it in like you're supposed to. I hope you're having an awesome time today. Let me know if you need any help. Thank you so much for paying attention. Goodbye, everybody.